Human timekeeping methods and devices. Human beings did not invent time. We learned to recognize recurring rhythms in nature, then created methods for recording, comparing, displaying, and transmitting those rhythms. This diagram presents 6 major stages in that long development. Natural observation, flowing substances, combustion, mechanical oscillation, electronic and crystal oscillation, and finally atomic and optical timekeeping. The central idea is simple. Every clock needs a rhythm that repeats reliably, a way to count the repetitions, and a way to show the result. 1. Natural observation. The earliest timekeeping method was direct observation of the natural world. Sunrise and sunset divided light from darkness and helped define the day. The changing phases of the moon supplied a longer cycle of about 1 month. The apparent movement of stars and constellations helped people recognize the hours of the night and the seasons of the year. Seasonal changes, guided planting, harvesting, migration, and religious festivals. Natural observation required no machine, but it depended on clear skies, local geography, and human interpretation. It was excellent for recognizing broad cycles, yet it could not provide the uniform, minute-by-minute precision needed by later societies. 2. Timekeeping by flowing substances. To measure shorter intervals without constantly watching the sky, people used substances that flowed at a reasonably steady rate. A water clock measured the rise or fall of water in a marked vessel. The word clepsydra is an ancient name for a water clock, literally suggesting water being taken away. An hourglass used dry sand or another granular material passing through a narrow opening. These devices were useful indoors, at night, and during speeches, work, or ritual activities. Their accuracy depended on careful calibration because water pressure, temperature, the shape of the opening, moisture, and grain size could all change the flow rate. 3. Combustion-based timekeeping. Another approach was to measure time through controlled burning. A candle clock used marks along a candle to indicate how much time had passed. An oil lamp clock estimated duration from the changing level of oil, while incense clocks used sticks, spirals, or specially prepared trails that burned at a planned rate. Combustion clocks worked in darkness and could sometimes trigger sounds or release small signals. They were practical for measuring duration, but not highly exact. Air movement, wick quality, fuel composition, humidity, and temperature could speed up or slow down the burn. 4. Mechanical oscillation timekeeping. Mechanical clocks introduced a major conceptual advance. A controlled oscillator combined with an escapement and a train of gears. The oscillator repeats a motion, the escapement releases energy in small steps, and the gears count those steps and move the hands. Early mechanical clocks used less regular regulating systems, but the pendulum greatly improved precision because its swings can be highly consistent. Portable balance wheel watches applied the same principle in a compact form. The marine chronometer was especially important for navigation. By carrying accurate reference time at sea and comparing it with local solar time, navigators could determine longitude. Mechanical clocks still faced friction, wear, temperature changes, and motion, but they transformed public life, navigation, science, and industry. 5. Electronic and crystal oscillation. Electronic clocks replaced many moving parts with electrical signals. Some electric clocks used the stable frequency of an alternating current power supply, while others used motors, coils, or electronically controlled oscillators. Quartz clocks made a further leap. A quartz crystal changes shape slightly when voltage is applied, and it also produces voltage when mechanically stressed. This piezoelectric effect allows the crystal to vibrate at a very stable frequency. A common watch crystal oscillates at 32,768 Hz. Electronic circuits repeatedly divide that frequency until they produce 1 pulse per second. Digital clocks then count the pulses and display the result numerically. Quartz technology is compact, inexpensive, and far more stable than ordinary mechanical clocks, although temperature and aging can still cause small drift. 6. Atomic and optical timekeeping. Atomic clocks use the extremely consistent frequencies associated with transitions between quantum energy states. The international definition of the second is based on the cesium-133 atom. 1 second corresponds to 9,192,631,770 cycles of a specific transition. Atomic clocks are essential to satellite navigation, telecommunications, scientific measurement, and the synchronization of large computer and power networks. Optical atomic clocks use transitions at much higher optical frequencies and lasers to interrogate atoms or ions. Because the underlying oscillation is faster, these clocks can divide time into even finer intervals. They are so sensitive that they can detect tiny timing differences linked to changes in gravitational height, revealing a deep connection between timekeeping and relativity. The pattern behind all 6 methods, the 6 stages, are not simply a list of old devices replaced by new ones, they reveal a common pattern. First, people identify a repeating or steadily changing process. Second, they stabilize it as much as possible. Third, they count equal intervals. Finally, they display or communicate the count. Astronomical cycles are enormous and natural. Flowing water and sand create controlled change. Burning materials convert chemical energy into a measurable duration. Mechanical clocks count swings. Quartz clocks count crystal vibrations. Atomic clocks count quantum transitions. At every stage, the goal is the same: to find a rhythm that is more stable, more uniform, and more precise. A thread running through civilization. Timekeeping made coordination possible on an ever larger scale. It organized agriculture, worship, markets, schools, navigation, factories, transportation, communication, and scientific experiments. Modern society does not merely read clocks. It depends on networks of synchronized clocks. The final message of the diagram is therefore important. Humanity did not create time. We continually searched for dependable natural rhythms, learned to count them, and built systems that could record, display, and transmit them. The history of clocks is also a history of observation, engineering, cooperation, and our growing ability to understand the universe.